Okay, so we'll go ahead and get started. I don't know if Alex, oh, no, Alex is not on, but I'm going to record this anyways. Yeah, so I'm going to post this online. So if you guys want to rewatch it, you can do that as well. So tomorrow we have the last stat seminar talk of the semester. So Deb Mayo is going to be chatting with us. She's going to be here in person. Should be a super interesting talk because she's not a psychologist. She's a philosopher of science. She's a statistician, and she's going to kind of talk kind of broad issues with statistical inference. So I think it should be a really good talk. So again, obviously the talks are open to you guys. If you want to attend, you can. It's the last one of the semester. So just throwing that out there. So before we jump into the material today, does anyone have any questions about last week's lab, questions in general about some of the things that we covered? Life in general, you guys doing okay? Ready for the break next week? Yeah, no, so it's typical to have class on the Monday before Thanksgiving, but I'm going to be in San Francisco, so you guys have the whole week off, so hopefully you guys will be able to escape and maybe go back home or at least just hang out here in Princeton. But I think it's canceled.
There's a rumor that
Oh,
It's usually canceled.
classes are on Tuesday.
what the heck?
I think those of us who are presenting got an email about like maybe rearranging things, so
Oh.
it's gonna be canceled.
Okay. Yeah.
Interesting.
It's like on the syllabus of class, but I really shouldn't.
I think it's stupid to have class during Thanksgiving week, so
Yeah.
yes. So hopefully it'll be canceled. You might be able to just email that. Can you just cancel it? Pretty please. So today we're going to be talking about transformations, and there's not too much to cover. So I know I've said this before that we'll get out early, but I'm hoping that today is the day that we get out early. So maybe the only time this semester will end early. But I have a link to the Cordo slides, or so the code for the slides. So if you want to follow along, I recommend doing that. You can download that from this link. So as I said, we're talking about transformations today. So transformations involve changing our predictor variables, our explanatory variables, or our response variables, right? So mutating them, changing them. And I want to talk about two types of transformations. I want to talk about linear transformations, such as centering and standardization. And I want to talk about nonlinear transformations like logarithms. And then I want to end class today by talking about polynomial regression. So this involves changing our predictor variables by squaring them or cubing them to account for nonlinearity in our models. So that's where I would like to end today, is talking about polynomial regression. So you might have the question, why should we transform our data? And there's a few reasons why we want to transform our data. The first reason is that we want to make our data more interpretable. So some transformations can help make our data be a little bit more sensible. We might do some transformations to put predictors on a common scale so we can compare them. Most of the time we do transformations to meet certain assumptions of our models, right? So our data might fail to meet some of those assumptions. So things like nonlinearity, non-normality, and non-constant error, so heteroscedasticity. So that's why we might do some transformations. That's kind of the biggest reason why we would do transformations, is because our data doesn't meet the assumptions of our model. So what I want to talk about first are linear transformations. So linear transformations just involve adding, subtracting, dividing by, or multiplying some type of constant. And what's important to know about linear transformations is that it does not change the relationship between those observations. It does nothing. So for example, if I had the numbers 1, 2, 3, and 4, and I just added 1 to each of those, that doesn't change the relationship between the variables, right? I'm adding some constant, the same thing, to each number. So that's important. It doesn't change the relationship in any genuine way. And there's two common types of linear transformations that we do. One is centering, and the other one is standardizing. So I want to talk about each of those in turn today. So to kind of highlight centering and standardization, I want to use a data set that we used a couple weeks ago on pitch and age. So let's go ahead and just load that into our environment. So if we go to R. Gonna load that bad boy in there. Awesome. So if you remember, this is the scatter plot of the data from the lab, right, where we looked at age and pitch, and the relationship is negative. So as age increases, pitch perception decreases. So can you remind me again what our intercept is, the interpretation of our intercept, B sub 0 just in general? How do we interpret an intercept term in the context of a linear regression? Just generally speaking, not in the context of this data. I don't expect you to remember.
It's just the y value when x is 0.
Yeah, correct, Abby. It's just the y value when x equals 0. In this case, the intercept is the mean when age is equal to 0, right? That's our intercept here. Well, that's kind of nonsensical, right? So age can't be 0. But even in that context, right, in our data set itself, we don't have any 0 points. Age is not 0 in our data set. So in this case, it would be nonsensical to have that interpretation. So what we can do is we can apply what's called mean centering. That's probably one of the most popular types of linear transformations that we can do. And what mean centering does is it basically changes that intercept. So now it's not when age equals 0, it's when age is at its mean value. So we've just shifted the intercept from all the way over here, all the way over here, which is the average value of age. So that's what mean centering does. So how do we mean center our data? So I wanted to walk through a couple different ways that we can apply centering to our data. So you have a couple different ways that you can do this. So our data set is called data. Let me put this over here. Let me cancel this so you can see it. So what we could do is we could do this manually by basically doing a mutate and creating a column. So when I center variables, I usually use _C, or you could use uppercase C to denote that you've centered that variable. So what we can do is we could just take age and we just subtract that from the mean age. And this essentially will center our variables. This is all centering entails. Again, it's just shifting that intercept point, right? So it's not age equals 0 now, it's age at its mean, because we're taking that mean and subtracting it from each value. So this is one way we can do this manually. The other way is by using a package called Data Wizard, and it's from the Easy Stats ecosystem. So let's create another variable from Data Wizard. So I'm just going to append DW for Data Wizard. They have a function called center, simple enough. And we just put in the variable we want centered. And this will create a centered variable, right? So in both cases, the manual way or the more automated way give us the same results. So essentially that's all that centering is. And then this pretty much highlights what I just went over, the different ways that we can center our data. And I'm gonna regenerate these slides and post them online so you guys can see how to do this for Wednesday's lab. So the most popular type of centering is mean centering, but we don't only have to do mean centering, right? We can actually center our data to whatever value you want. Obviously, it should be sensible and some type of useful value. So you might want to set it to the smallest possible value in the data set, but it doesn't only have to be mean centering. But mean centering is the most popular centering technique. So let's go ahead and fit our model with the centered age variable. So that's what I've done here. And then what we have here is just the output for our linear model here with age centered. So let's go through the interpretation of each of these terms. So when we're looking at the intercept B sub 0, how do we interpret this estimate here? What does this estimate represent now that we have centered our data? Gonna back to here. Anyone? this. Because that. Yeah. All right, so we have our intercept of 175. What does that value represent?
Is it the y value where when the age is the mean?
Yep, correct. Yep. So that is what our intercept now means. So it's not, the value of y when x is 0 years of age. Now it's the value of y when age is at its mean. So that's what our intercept now means, that we centered our variable. So that's what our intercept is. So what about our slope estimate? So negative 0.69. So again, I don't expect you to remember the lab that you did several weeks ago, but hopefully you'll remember that this estimate hasn't changed. This is our same slope estimate. So in terms of interpretation, we can interpret this the same way, regardless of if the variable is centered or if it's not centered. So it's for every 1 unit increase in age, there's a 0.69 decrease in pitch perception. So let's go ahead and write that interpretation down here. Awesome. So you might have the question, when should we center our data? So you should center your data when there is not some type of meaningful 0 point in your data set. So maybe your variable just doesn't contain 0, or it might be nonsensical, like, the age equals 0 case in our example. But if 0 is meaningful in your data set, you don't need to create a centered data column, right? Or you don't need to center your variable. But we're going to see later on at the end of class that centering can actually help with multicollinearity issues. So if you have two variables that are collinear with one another, centering can actually help reduce the correlation between those variables. So my motto essentially is when you're in doubt, you should always center. Centering is not going to harm your model in any way. It's not going to harm any of the interpretations that you have. Again, it doesn't change the relationship between those variables. All it does is change the interpretation to make it a little bit more sensible. So if you have continuous variables, just center them. It's not going to do any harm. That's kind of my suggestion. All right, so is there any questions on centering your data before I move on to the next type of linear transformation? Thumbs up, sideways.
Doesn't that now make it kind of more confusing though? Because and now the 0 for age is not 0.
Well, so it's still 0, but the 0 point has just been shifted or changed to the mean value. So now, when we interpret the intercept, so when we talk about interactions, it'll probably be a little bit more apparent why that this would be important. But again, it's just in terms of sensibility. So if you don't have a 0 point in your data, why would you care about the intercept at 0, right? When an actual data point is 0. So what mean centering does is it just changes that 0 point to something that's more meaningful, which is the mean. And there's values. So in this particular data set, there's not really any data points that are kind of exactly the mean, right? But it's more logical. It's more in the realm of possibility that you could have a variable that value, right? Instead of age equals 0. Again, just in terms of sensibility and interpretability, that's why we would center our variables. And you cannot center your variables. I mean, it'll become apparent why we might want to center them when we're dealing with interactions, because there's high multicollinearity. So we could just center it. And again, you would just change it. Instead of talking about age equals 0 years of age, you just do age is at its mean. That's kind of just a slight change in interpretation. So now I want to talk about a different type of linear transformation, and that's standardization. So far we've been talking about little b, and little b is our unstandardized regression coefficient. And the interpretation is for every 1 unit increase in x, there's going to be some unit increase or decrease in y. So there's another type of coefficient that we haven't talked about, and that's beta or big B. And this is the standardized regression coefficient. And in the literature, a lot of times people talk about little b and beta as being the same thing. They are not the same thing. We need to make sure that when we're talking about these things that we differentiate the two. Little b is unstandardized, big B or beta is standardized. And what standardization does basically is take X and remove its original units and replaces that with standard deviation units. So instead of saying for every one unit increase in X, we say for every one standard deviation increase in X. Again, we're changing that to standard deviation units. So why might we want to standardize our predictors? So if we're working with a model with lots of different variables in it, a lot of these variables will be on different scales or different metrics. So standardization can help us compare within models, right? Because we're getting rid of those X units now. Everything is on standard deviation units. And a lot of folks, what they'll do is they'll use this as a way to measure importance of a variable. So if your beta is, 5.43 for one variable and your other variable beta is 9.32, what we can say is that the second variable has a larger influence on the DV than the other variable. So a lot of people will do this when they standardize their variables. And to standardize your variables, it's very simple. And this is something that we already went over. Essentially what we're doing is z-scoring our age variable here in this context, or just z-scoring our variable in general, right? So we're taking our centered mean. So we're taking our observation and subtracting the mean from that and then dividing that by the standard deviation. That's essentially just z-scoring our data to where now the data has a mean of 0 and a standard deviation of 1. And I've taken the liberty to z-score the variable, the age variable. And I want to point out that if we look at these scatter plots with the centered variable or the standardized variable, the scatter plots are essentially the same. So this is basically the same as this, right? So they're exactly the same. The only thing that's different now is that the age variable is in terms of standard deviation units, or the other ones are on more of the original metric, or we're centered. And also important to note here is that, again, when we're doing the standardization technique, the mean is 0 now. So it kind of has the same function as centering, where the 0 point is going to be the mean of that particular variable. So how do we standardize our variables? So let's go back to R. So there's several different ways that I want to kind of outline to standardize our variables. So if we could take our data set, we can do this manually. So I like to append the underscore Z to standardized variables. So if you remember the formula for Z scoring, we take our age variable and then we subtract the mean of age. So again, this is centering. But now what we're going to do is we're going to divide it by the standard deviation of age. And this will standardize our variable to where there's a mean of 0 and a standard deviation of 1. So this is the manual way to do it. We can also use our data wizard package. And there is a function called standardize. They have the British spelling and the American spelling, so just use whatever you like. So there is a function called standardize that will standardize our variables. So let's run that. So again, we see that these are comparable, the manual way and the data wizard way. And then if you are partial to base R, there is a base R function, which is called scale, that will also standardize your variable for you. So again, different ways to do the same thing. So just choose which method you like the best and stick with that method. And then this just reiterates what I just went over, how to standardize the variables, so you have that. So let's go ahead and fit a model with our standardized age variable. So this is the summary output here. And what I want you to notice is that now that we're working with standardized variable, we're not using little b sub 0, we're using beta sub 0. So that has changed. So how do we interpret our intercept term in a standardized model where we've standardized our predictor variable? What does b sub, how do we interpret b sub 0 here? It's the same thing as centering. Yeah. Yeah. So basically what beta sub 0 represents is the value of y when age is at its mean. What about beta sub 1? So our estimate here. How do we interpret this coefficient? And this is not the same as with centering.
Is there a change in y when x change 1 instead?
Yep. Great. Yep. So when we so a 1 unit or a 1 standard deviation increase in x leads to some change in y. So yeah, so for every 1 standard deviation change or 1 standard deviation increase in x, I should say increase, there's some change in y. And here that change is negative 9.19. So for 1 standard deviation increase, there's a negative 9.19 decrease in pitch perception. So that's a little different than the standardized model here. So what I want to do here is I want to compare the different outputs. So with just a standard model, a centered model, and a standardized model, and then show the similarities and differences between those models here. So if we just fit a regular regression model with age regressed onto pitch, this is our output here. And the intercept is the value of y when x is equal to 0, right? 215. And then our age is the slope, right? So for so 1 unit increase in age leads to a 0.69 decrease in pitch perception. That's our standard interpretation where we haven't done anything to our variables. When we run a centered regression model with age, the intercept is now the value of y when x is at its mean. So it's 175. And our age centered slope is the same as the standard model. So an unit increase in age leads to a 0.69 decrease in pitch perception. And then when we standardize the model and run that, the intercept is the value of y when x is at its mean. And the age variable now is for 1 standard deviation unit increase, there's a negative 9.19 decrease in pitch perception. So what I want to highlight here is that when we standardize or where we're centered, we're just changing the interpretation of the coefficients. So when we're talking about centering, we're talking about just changing the interpretation of the intercept. And when we standardize, we're talking about changing the interpretation of our x variable, right? So instead of a 1 unit increase on the x variable, it's a 1 standard deviation unit increase on the x variable. And something that I want to highlight here is that it does not change statistical inference or our model in any meaningful way. So we could look at our test statistics here, and they're all the same across these different models. The test statistic is the same for the centered variable, for the centered variable, and for the standard variable. They're all the same. It does not change our model in any meaningful way. So are there any questions about standardization? Thumbs up, get it, middle, down. So now I want to talk about nonlinear transformations. So as I said, linear transformations don't really change the model in a meaningful way, but nonlinear transformations do change the model in a meaningful way. So when we apply a nonlinear transformation, that's going to actually affect the data points differently. So again, it changes the relationship between those data points. And the most common type of transformation is the log transformation. And we usually use nonlinear transformations to make our models more in line with assumptions. So if there is a nonlinearity violation, or excuse me, if there's a linearity violation, or there's a violation of homoscedasticity, then we want to apply probably a nonlinear transformation to our data. A linear transformation is not going to do anything about that. So the most common type of nonlinear transformation is the log transformation. And basically what log transformations do is it describes changes in terms of multiplication. And it answers the question, how many times do you have to multiply some type of base number by itself to get another particular number? And the logarithm is inversely related with exponentiation. And hopefully you can see here, what we do essentially is we take some number and we log it. And in R, we can use the log function to log our variables. And R uses the natural base log, which is 2.7182. That's kind of technical stuff that's not really that important. But the reason why we want to use this is because it makes our regression more interpretable. So we can actually talk about percent increase or proportion change when we use just the standard base log of 2.7182, because there's a relationship between those two. So again, kind of technical stuff that's not really that important, but using this natural log allows us to talk about things in terms of proportion change, which I think is very useful and makes things just easier to grasp and understand. But essentially what we're doing here is we take some number and we log it, and that gives us an exponent. And what this does is it tells us how many times we need to multiply this base number here, which with the natural log, it's 2.7182, right, to get some number. That's essentially what we're doing here and how these are related. In a nutshell, what exponentiation is doing is it's taking small numbers and growing them larger. So we can take 10 to the first power, that gives us 10, 10 to the second power gives us 100, 10 to the third power gives us 1,000, and so forth and so on, right? We can see that small numbers growing larger when we exponentiate them. In R, we can use the exp function to exponentiate our numbers. Conversely, logarithms take large numbers and shrink them. And this is why this is so often used. It's so powerful. We could take log 10 and that gives us 2.30. We could take log 100, that gives us 4.61, log 1,000, log 10,000. And you can see here that those large numbers have kind of shrunk in size, right? And as I've already stated, we can use the log function R to log our variables. And what log transformations do is they track the order of magnitude. And what's really cool about using the log transformation is that the larger numbers shrink more than the smaller numbers. So there's this kind of compression effect where if we have larger values, that moves them closer together. So I've highlighted that here with just a vector of reaction times. These don't have to be reaction times. This is just what I usually work with. So I have 600, 650, 700, 1,000, and 4,000. So we can see how far apart 1,000 and 4,000 are, right? Well, if we log those RTs, which I'm doing here, we now get a vector of log RTs. And hopefully now you can see that they have kind of compressed together, right? So now this 1,000 and 4,000, the difference has kind of lessened, right? From 6.9 to 8.29, right? So again, logging has this compression effect. And what I think is so cool is that we can actually take the exponentiation of these log RTs and get back our original RTs. So I've just logged these RTs. I can take the exponentiation of those logs, and then I get back our original vector of reaction times. This is going to be important when we talk about interpretation of our regression coefficients. So this is kind of a demonstration of this in action. This projector sucks, but those are words that are on the actual scatter plot instead of data points. And these words have both reaction time, so how long it took to respond to them, and it also has their frequency. Words with higher frequency are more well-known words, and they usually are responded to faster. And words that have lower frequency are less known words, and those take longer to respond to, as kind of highlighted in this figure here. So this is the raw data. Nothing has been done to that. And we can kind of see that there's some kind of scatter, right, where some of these words are kind of further away from the words over here. We can take the log of those variables, and what we see now is that there's this compression effect where now the words are kind of more equidistant from one another, and they're kind of a nice linear pattern here. So it's really kind of magic what these log transformations can do to aid in interpretability. So what I want to do is I want to talk about transformations to the y variable or our response variable. And we usually transform y to make our predictor variable, excuse me, not our predictor variable, our response variable more linear. We do these y transformations to make them more normal, and these y transformations can help with heteroscedasticity. In my field, I work a lot with reaction times, and reaction times are always positively skewed. And that's kind of depicted here. I took this from a paper. This is not right. I don't know why this is slow and fast. But what we usually see in reaction time data is that there's, some folks that just take a really long time to respond to something. And that creates this positive skew that you see here. What we can do is we can log transform this data, and now our distribution is more normal in shape. So the most common type of y transformation is the log transformation. There are other types of transformations that you can do. There's things like the square root transformation. There's an inverse transformation. I'm not going to spend time talking about these other types of transformations because I think that it makes interpretation really difficult. And really the logarithm transformation is really the most straightforward to interpret in the context of a regression model. You might want to apply some other transformations if the log doesn't work, but interpretation goes down when you start using these other transformations. If your main goal is prediction, then have fun applying whatever transformation you want to make your data more normal. But in terms of interpretation, it's going to be very hard to do so. So the log transformation is probably the most straightforward. And this is the one that I mostly use. Do any of you guys use different types of transformations on your data? Or have seen that in the literature? Is it common in your field? I know for Abby, yes. Anyone else? No? But so to highlight transformation of the y variable, I had to search far and wide for an example that actually fit the criteria that I wanted. I couldn't find a psych example, so I apologize, but I found this one, and I think it does a pretty good of demonstrating what y transformations can do for our model. Here, there's two columns. There's an age column, and then there's a rate column, which is respiratory rate. And basically, high respiratory rate can indicate some type of respiratory infection in children. So that's the data that we're going to look at. So I got this from the Sleuth3 package, and the data is just labeled EX0824. And this is what the data set looks like if we graph it. So this is a scatter plot where we have age on the x-axis, and then we have rate on the y-axis. And we see that there's a negative relationship where as age increases, respiratory rate decreases. So the chance of a respiratory infection seems to go down as you age. So because we're going to log transform our y variable, our linear model formula changes a bit. So now we're not taking y hat equals b sub 0 plus b sub 1 times x. Now we're taking the log of y hat equals b sub 0 plus b sub 1 times x. So our y variable has changed here. And for those of you that do logistic regression or have done logistic regression, this is essentially the model that you fit with a logistic regression. So the interpretations that we're going to go over today extend to just fitting a binomial logistic regression. And we're not going to talk about logistic regression this semester, but we're going to talk about logistic regression next semester. And all of this is going to carry over. So when we are fitting this model with our log y variable, we don't want to interpret the coefficients in terms of log y. I mean, you surely can. I think that makes interpretation a little bit more difficult. So what we can do is we can actually back transform our log y variable to our original units. So if you remember here, where we logged our RTs, we just have to take the exponentiation of those RTs, and then we get our original scale back. So that's what we do here. We just take the exponents of our coefficients, right? We take the exponentiation of the intercept and the slope, and we get our original y variable. So we can interpret it back on the original y scale, which is extremely useful. So I'm going to come back to this. So let's go ahead and just run a model with our raw variables that have not been transformed. And let's check our assumptions of this model. So I have two assumptions here that are most impacted, or that would be most impacted, which would be homogeneity or homoscedasticity and normality. So this is just a raw model, nothing has been transformed. And if you look at our model assumptions here, we can see that the homogeneity assumption has been violated here. We can kind of see this fanning shape kind of closer to the end of the fitted values, right? And that like reference line looks a little bit raised. So this indicates that there's some, heteroscedasticity in our data. If we look at normality, we see that there is some skew here. So our data is definitely not normal. So we can go ahead and fit a log Y regression model, and we can see if that helps with our model assumptions. But before I talk about the model assumptions, I want to talk a little bit about interpretation of the actual coefficients themselves. So when we log our Y variable, what we're going to do with our coefficients is we're going to exponentiate those coefficients, subtract 1 from this, and then multiply it by 100, so we get a percentage. So essentially we talk about percentage increase or decrease when we're working with log Y variables, or when we're working with log X or predictor variables. So for our coefficients now, for every 1 unit increase, or 1 unit increase in the predictor variable, our dependent variable is going to increase or decrease by a percentage. So that's how we're going to be interpreting our regression model now. And when we exponentiate our coefficients, if the exponentiation value is greater than 1, we just talk about percent increase. If it's less than 1, we're going to talk about percent decrease. So let's go ahead and fit our models. So there's two ways that we can include a log Y variable. So we can just include it in the model like I've done here, right? We could just use our log function and just log the rate variable. Or you can actually append it to your data frame. So you can just, create a new column that's the log of rate, and then enter that into the model, whatever you prefer. So I've fit two different models here. So this model here, I have not exponentiated the coefficients. So Tidy has this really useful function called exponentiate, and I've set this to false. So essentially what you're going to get is the log Y variable interpretation. So in our actual summary report, this age variable here, what we can say is for an increase in age, or a 1 unit increase in age, there is a log 0.01 change in Y. So not that intuitive, right? If we're talking about log Y here. So what we can do to make it a little bit more interpretable is just exponentiate those coefficients. So within the Tidy function, we can just say exponentiate equals true, and that's just going to exponentiate our coefficients for us. We can do this by hand. So I can take this value right here in R, right, and just exponentiate that, and I get the same thing, 0.98, right? So this just does this for us. So how do we interpret this model? So I have the interpretation of each of the coefficients here. So in terms of the intercept, what we want to say is that the mean respiratory rate for a newborn child, so when age equals 0, is expected to be 46.759. And how we got this is we just exponentiated this 3.84 from our original model here. So again, remember, exponentiation puts things back on the original Y scale, right? So that's what we're doing here for the intercept. When we talk about age, our slope estimate, what we're going to say is that for an increase in age, the respiratory rate is expected to decrease by 2%. So why is it decreased by 2%? Because this exponentiation, or this exponential value, is less than 1. So we talk about decrease instead of increase here. So again, this is basically in a nutshell how you would interpret these log models, and this extends to logistic regression as well. So I think it's pretty useful to know how to interpret these models like this. So just real quick, so how did we get 2% here? We just subtracted 1 from 0.98 and then times that by 100, and that gives us 2%. So that's how we got the percentage. And I like to talk about these models in terms of percentage. So that's why we talk about increases or decreases by 2%. So we can go ahead and we can check our model assumptions again for the model with our log rate variable. And what we see is that our model has vastly improved. So we can see that this reference line is a little bit more horizontal now. Before it was kind of raised a little bit. Now it seems like the errors are pretty constant, which is good. And normality looks a lot better now. So our variable looks a lot more normal than it did before. So again, this is kind of highlighting how logging your DV can help meet these assumptions. So are there any questions about log transformation of Y variables? You'll have some practice doing this on Wednesday too. So if more questions come up, you can definitely ask. So now I want to switch focus and talk about transformation of X variables or predictor variables. So you might plot the relationship between X and Y, and you might observe something that looks like this on the screen, where there's kind of this curvature here. So this indicates maybe that there's some nonlinearity in your model. So you want to maybe make it more normal and more linear. So what you can do is you can log transform that X variable, and transformation of those X variables help make it more linear and more normal. However, it does not fix heteroscedasticity. Heteroscedasticity is involved with the residuals and not with the X values. So that's also important to note. If you have non-constant errors, transforming your X variable is not going to do anything to help with that. But if you have some non-linearity in your model, or maybe some non-normality in your model, transformation of the X variable could help. Why did it go all the way over there? Yeah. So when we log our X variable, the formula that we use changes a little bit. So now we have the predicted value of Y, right, equals B sub 0 plus B sub 1 times the log of X. And when we're using log transform predictors, what we're going to do is we're going to divide the coefficient by 100. And that's how we're going to interpret our model. So instead of a 1 unit increase or a 1 standard deviation unit increase, we're talking about this in terms of percentages, right? Makes it super simple and super easy. So we're talking about a 1% increase in the independent variable, changes the dependent variable by the coefficient divided by 100 units. That's one interpretation. The other interpretation is we can talk about this in terms of X% increase. So it doesn't have to be 1% increase. It could be a 20% increase. It could be a 30% increase. So in order for us to do that, what we just do is we take that coefficient and we just we'd multiply it by 1 times 0.20. And I have a little note here that if you multiply a number by 1.22, it's the same thing as increasing that number by 22%. So again, we're just taking into account this X% increase. If you just want to talk about this in terms of like a 1% increase, you can also do that as well. But sometimes it might make more sense to talk about a 10% increase or a 20% increase. So let's go ahead and fit our model, but this time we're not going to do anything to the Y variable. We're going to transform our predictor variable. We're just going to log that. Similar to before, you can log it within the actual formula itself, which I've done here, or you can just append a new column to your data frame with the log of age as the variable, whatever you prefer. And this is our summary report for this regression that we just ran. And I have the interpretations of each of these terms here. So when we're talking about the intercept value, when we've logged the age variable, it's the mean respiratory rate for children who are 1 month old. So we can't take the log of 0, we have to take the log of 1, and that equals 0. So that's 50.135. When we talk about the slope estimate, we could talk about it in terms of a 1% increase, right? So if we're talking about it in terms of a 1% increase, we can say that for a 1% increase in age, the respiratory rate decreases by 5.98. Or we can talk about it in terms of the age doubling. So if the age doubles, so going from 1 to 2, we expect the respiratory rate to decrease by 4.146 breaths per minute. And to get that, we just take our coefficient and we multiply that by the log of 2, because we're basically going from 1 to 2. We're doubling it. So that's how you interpret a regression model where you have the x variable transformed, or log transformed at least. So there's other types of x transformations that we can use. We could use the square roots, we could use the inverse transformations. And as I said, this just makes things harder to interpret. So I would recommend probably against doing those other transformations, and just stick with the log, and hopefully that helps. We could also log our x variable, and we can log our y variable. And if we were going to do that, then the interpretation would just be in terms of percent increase for both variables. So for an increase in the x variable, there's a percentage increase in the y variable. And I have some examples here of how you would interpret that. So if our coefficient was 0.198, we could say for every 1% increase in the independent variable, our dependent variable increases by 20%. So I think pretty intuitive. We could also talk about it in terms of percent increase, right? So instead of a 1% increase, we could talk about it in terms of a 20% increase. And if we were going to do that, we would take our coefficient, and we would basically power that to our 1.20. So we're going to increase it by 20%, subtract 1, and then multiply that by 100. So what we're doing here is we're just calculating 1.20 to the power of the coefficient, subtracting 1 and multiplying by 100 to give us a percent change related to the 20% increase in the x variable here. So when should you log transform your data? So hopefully you would log your data if it's theoretically motivated, if it's common in your field. So it's very common in linguistics and psychology. I use log transformations a fair amount, but I guess in kind of recent work, I've kind of abandoned the log transformations and started just fitting models that, better fit the data shape. But log transformations are still fairly common in psychology and linguistics. You should log transform your data after you look at your data. So you might see that it's nonlinear, you might see that it's not normal. In that case, you might try a log transform to see if that will make the data more normal, make it more linear. You should not log transform your data if you have zeros or negative values in your DV, because you can't log transform those. So if that is your case, then I would try to look for a different model to fit, or maybe some transformation that would work for your data set. But log transformations would not work in that case. So are there any questions about log transforms? So my recommendation would be to read the chapter that I assigned for this week. I think that will help solidify things. There's lots of things in there that's not really relevant for us, but the things that they do talk about in relation to standardization and centering and log are really, really good. There's other stuff you could gloss over, but if you just read those parts that talk about what we talked about today, I think that will really help with the understanding of all these transformations. And on Wednesday, we're going to have a data set that we're going to work with that's going to have you log transform some data and also interpret it. So hopefully it'll make a little bit more sense when we apply it to an actual example. So now with the rest of the class time, I wanted to talk about polynomial models. So we just talked about transforming our predictor variable, right? If it's nonlinear, but sometimes we want to embrace nonlinearity in our model. And the way we can do this is by fitting a polynomial model. And a polynomial model essentially accounts for this nonlinearity in our model. And it does this by raising our variables to different powers or degrees. And so what I have here is kind of just an outline of the different powers that we can raise our variable to. This says degree, but we can also say in terms of power. So if we raise our particular variable to the first degree, we're just talking about a linear trend. So this red line here, that's all that means. So if you have one predictor variable in your model, that's already raised to the first power, so you don't have to do anything with it. But we might want to raise it to the second power. If we raise it to the second power, we get this quadratic function here in green. So this would account for this type of pattern in your data. We can raise it to the third power, and this would be this cubic function here. So if your data looks like this, you might want to fit a third degree polynomial. You could do fourth degree, fifth degree, sixth degree. This type of stuff is very common in like the longitudinal stuff that I do, but it doesn't have to be longitudinal to get some of these patterns. So again, we can fit this nonlinear polynomial model to our data. So let's work with a particular example. So this example is very simple, and I think it highlights this nicely. So let's look at happiness and hours worked. So I have hours worked here and then a measure of happiness here. So if we graph this data, if we visualize this data, this is the pattern that we get. And I've just kind of stuck a linear line there. Do you think a linear line fits this data well? No, thumbs down. It does not do a good job of explaining this data. So we probably wouldn't want to just fit a linear model to this data. What we can do is we can just kind of extend our linear model equation that we've been using, right? And all we're going to do is we're just going to include a quadratic term. So this is pretty quadratic in shape. So I think it's sensible or reasonable to include a quadratic function in this particular data set. So to do that, all we're doing is we're just adding another x variable that's squared. And what I've highlighted here is how we could just append it to our data frame, where I've just taken the time variable and I've just squared it. And then that will take into account the quadratic function or the quadratic shape in our data. I think it's called, yes, it's called hours. Yeah, so I just squared that and added it to our model. So let's go ahead and just fit our linear model with just hours instead of our hour squared term and just see what happens. So here's the linear model for just hours. So this is just a linear trend. And these are our estimates. So I have the summary here, and then I also have the model summary. So we have our estimate or intercept. So this is the value of y when hours is at 0. It's 48.45. And then we have our hours term, and we see that this is not significant. So there is no linear trend in this data. We look at the model fit here, and we see that our R squared is about 0.04. So 4% of the variance could be explained by this, and it's very low. So this does not do a good job of capturing our model at all. But let's go ahead and let's put in our quadratic term, our time squared term into the model. So now we have our intercept, we have our linear term, which is just hours, and then we have our time squared term here. And then we could look at our R squared, and we see that the R squared is now 0.96. So 96% of the variance could be explained by our predictor variables, mostly coming from this squared term here. But there's something odd going on here. Does anyone see anything odd with these estimates? Something that seems off? So I mean that I think that's one. So if you notice in our last model, hours wasn't significant, right? And now it's significant. So that's one thing that's kind of odd. Any other things people notice? I'm just hovering over this intercept here.
It's just a very negative intercept.
Well, so can we have negative hours? No. So yeah, so this is kind of nonsensical and this is weird. So this is the problem that I talked about last week with multicollinearity and this idea of bouncing betas. So what we're doing here is we're basically superimposing collinearity in our model by including this squared term into our model. If we look at the correlation between hours and hours squared, they're correlated probably by like 0.96. They're highly correlated with one another. And one of the consequences of this collinearity is imprecise estimation, right? Because they're all vying for this unique variance, right? And that can cause our estimates to do funny things like it's doing here. So we could check our collinearity for this model, and we see that our collinearity measure, our BIF, is 23.78, which is huge. So that is beyond our threshold of 10. So these are highly correlated. So what do we do about this? Well, we can center our variables, and that will reduce the correlation between these two variables. So the beauty of centering. So my recommendation, if we're going to be entering in like cube terms or quadratic terms, is to first center our variable, then square that centered variable, and then center that squared variable. And then we can refit the model where we have happiness, and then we have our hours centered variable, which is our linear term, and then our hours squared term that's already centered. Then we can check our collinearity, and what do we see? The collinearity has gone down. Now there's a low correlation. There's no cause for concern. So let's go ahead and fit our model with their centered terms in there and see if our inferences are a little bit more reasonable. And I think that they are more reasonable. So our intercept now is not negative, it's 58.18. So this is the value of y when hours and hours squared are at their mean. Then we have our linear term that's centered, and this is non-significant, which makes sense. There does not seem to be a linear trend in our data. So that's not significant anymore. And then our squared term is significant, and it's negative. So in terms of, these type of models with quadratic terms and cubic terms, the sign of the coefficient is important. In terms of the quadratic function we are fitting, or excuse me, in terms of the quadratic equation we're fitting, if there's a negative coefficient, that means that the data is more U-shaped. If it is positive, that means that it's more inverted U-shaped. So if we go back to look at our model, this is a quadratic line that's fit over the data. It fits the data so much better, right? It fits almost all the data points. They're fairly close to the line. It's a much better model here. But we can see, again, we have this kind of inverted U shape here. And then that is denoted by the coefficient estimate. So.
But can't we just fit a model without the linear part?
Good question. And I'm going to talk about that right now. So what we could do is we could fit a model with all of our terms in it, right? So our linear term, our quadratic term, if we have a cubic term, we can fit that model all together, right? What's commonly done is a thing called model comparison, where what we do is we compare a model with the lowest term in it. So we can compare a model with just our linear term. We compare that to a model that has our linear term and our quadratic term. And then we can also compare it to a model that has a linear term, a quadratic term, and a cubic term. And we can compare all these models to see which one fits the data the best. So that's a model comparison approach. So we haven't explicitly talked about model comparisons in here, but we've been doing model comparisons. So when we talk about the F-test, what is that comparing? What two models is the F-test comparing in a linear regression? Yeah, so we're taking a model that has all of our predictors in it, and we're comparing it to a model that has no predictors in it. But that's not the only comparison we can do. We can essentially do whatever comparisons we want. And this applies to polynomial regression. This also can apply to whatever type of regression you're using here. So what I'm showing here is that we're taking a linear model that just has hours in it, and I'm comparing it to a quadratic model that has hours and the quadratic term in it. And then I'm just doing an ANOVA that compares these two things. And we get our ANOVA table, and it gives us our F value and our sums of squares and the significance of it. But we can see here that our F value is 184, and it is significant. So how do we interpret this F value? Well, if it's significant, we say that the less parsimonious model, or the model with more degrees of freedom, is preferred. Same thing as if we were going to compare the model with all of our predictors versus the empty model, right? But now we're just comparing a model with a linear term with a model with the quadratic term with it. So in this case, a quadratic model is much preferred over a model that does not have that quadratic term in it, right? If our F value was not statistically significant, then we would say that a quadratic model is not warranted and that we would just go ahead with a linear model. But going back to Renata's point here, you were talking about just adding a quadratic term into your model, right? So it's common to include lower level terms in your model. So if you're going to include a quadratic, you should include the lowest term in there, which is a linear term. So I probably would not just fit a model with just a quadratic in there. I would fit it.
But then if you see that the linear is not significant, then you can don't use it anymore.
So I would just say, so I wouldn't fit a model with just the quadratic term in it.
Even if the linear is
Yeah.
not significant.
Yeah, so I wouldn't drop that from the model. I would include that in the model still.
Is that even is that? That's conventional.
That's conventional to just keep the lowest order terms in there. So I would not get rid of it. It's like the same thing. So if we're talking about like interaction terms, so like you wouldn't fit a model with just the interaction term and not the individual effects, right? You'd want to include those individual effects and then the interaction between those two. And that'll become apparent in the next couple of weeks when we talk about interactions. But usually it's convention that we include those lower order terms.
Even if like it's the same variable, like the same, it's hours and hours
Squared.
squared, yeah.
Yes, I mean, so like it would be the same interpretation, right? I guess if you just like got rid of this variable, right? And you're just looking at the times the squared variable. So I don't know if there'd be like drastic changes in the interpretation, but I don't see why it would hurt to include. What you'd want to see is that the linear term doesn't do a good job, but it's probably the case where maybe there is a linear term. So like stuff that I do, sometimes there's a linear trend and there's a quadratic trend. We want to interpret those two things. So in the case of this example, right, we can say that hours, so happiness increases up to a certain hour, and then it decreases as you work more and more and more hours, right? So we can interpret it that way. In this case, there's not a linear trend, but there might be a linear trend, and we want to include that in our model. But I think what you're saying is if you run the model and the linear trend is not significant, you might just want to like just take that out of the model and rerun it.
Yeah, and like if the x is the same, like if it was for another
Yeah.
variable, I think
Yeah.
it make more sense
Yeah.
to keep, but
Yeah.
like as it's also hours.
Yeah.
And I tend to think of the relationship between the
Yeah.
y and hours.
Yeah. So like theoretically, right, you might just want to include the quadratic term and that's it. So in that case, you could probably do something like that. I think as long as it's like theoretically motivated, it should be fine. Like in practice, I just include the linear terms and the quadratic terms and just interpret them from the model. If they're significant, then they're significant. If they're not, then they're not. So just as kind of a recap here, in terms of improving the coefficient interpretability, right? We wouldn't do logarithms or polynomials for that, but we would standardize and mean center our variables. To make sure that our model meets our assumptions, we would do things like logarithms and polynomials. To improve model generalizability, we would do things like logarithms and polynomials or use them. And to make the actual predictors more comparable to one another, we would standardize our variables. So this is kind of just a nice table that kind of encapsulates all the stuff that we talked about today. So use it for your reference. So Wednesday, we have a lab that's going to cover some of this stuff. So I think the lab is going to be pretty straightforward, where you're going to be given a data set from a paper, and you're just going to standardize the variables. You're going to log, transform some of the variables, and interpret them. Kind of similar stuff we've already been doing. Then after break, we're going to start talking about interaction. So we're going to talk about continuous by categorical, continuous by continuous, and categorical by categorical interactions. And that should take us to the end of the semester. And then we get a long winter break, and then we're going to start with advanced stats stuff. So I can't believe that there's only a couple weeks left of the semester. Insane. Went by really, really fast. So are there any questions, comments about any of the stuff we covered today, things in general?
I'm kind of wondering, like, what if you have more than one predictor variable, and you're doing like the polynomial?
Yeah.
Do you have to do it for every variable?
So it depends. Like I would look at the relationship between X and Y and see if there might be a quadratic, but you don't have to square every single thing in your model.
Okay.
So I might have something like, let's say age in the model or something, and I might not want to square that. Yeah, just leave that there, right? And then you'd get a coefficient here, right? You'd get this hours, the squared term, and then you get age, and you can interpret that as you would interpret the other coefficients, right? Increase in age leads to decrease or increase in happiness, stuff like that. But yeah, you don't need to square or cube all the other variables. So if there's no other questions, you guys are free to go. We ended early, so.
Now I
Yeah.
have a MacBook.
Oh, okay. That's not a weird cue. Okay, good, excellent.
It's like, it's related to the project because the data that I will use in the project is like the data that I'm working
Yeah.
now in my research. And I'm in a